if it was 2009 when Mike Cook was saying this, I'm sure I was doing it in 1999 and probably 1989 and 1970. Well, this is an old story. It's a scratch record, goes around and around. But if you say in the last 10 years or so, so we had the banking crisis 10 years ago, I think more or less this week. And in the intervening period, we've probably gone from being, let's say, pessimistic to realistic as engineers. I'm going to invite people to be optimistic for the next 10 years. So all this is about optimism. Because even though the record's been going round and round, eventually I'm hoping to take the needle off and put another record on the turntable, and it will be a different record, and it will be much better. This is a quote from a book written by a structural engineer in 1956, W.E. Bowman, who was a structural engineer, lived in Guildford. And it's you'll see why I've chosen it, but it's when you have a hunch that something is going to happen, you get this little feeling in the back of your neck. And this is a feeling I've been having, as I said, since 1999. I really quite like the hunch to be realised. And some of these things, Ian's already given my talk, actually, more or less. But what is engineering nowadays? Well, is it science? I'm going to put these up as a refresher for those. Many of you have seen these definitions before. But is it science? Well, science is something where you take the world, you look at the world, you bring it into your head, and you try and come up with an idea. It's an external to internal process. You try and come up with an idea which maps to what you see or what you find. Engineering, as Ian just said, starts inside the head and puts something in the real world. So makes the world conform to our ideas. It's the opposite of science. You use science for engineering, but they're not the same. They are quintessentially 180 degrees opposite intellectual processes. And it would be really good if people who are involved in the education of engineers and engineers themselves got that joke.
What did the people do who made this building and others like it? They took a dead heap of stones, which is not a cathedral, and they turned it into a cathedral by exploiting the natural forces of gravity, the way the stone had lain, the brilliant invention of flying buttress and arch and so on. And they created a structure out of the analysis of nature into this superb synthesis.
So that was Jacob Bronowski speaking nearly, well, I'm not very good at sums, 50 years ago, let's say nearly, and about the construction and the design of the cathedrals. And again, it echoes what Ian was just saying. And he said it, honestly, he said it better than I've ever been able to say it and anybody else. They created a structure out of the analysis of nature into a superb synthesis. Fantastic distillation of what engineering is about. And what he also says in that, although we didn't quite get there, is they did it in a form which touches people emotionally. And I think we have to remember that what we do goes on planet Earth. It's a physical thing. The people that we design for are affected physically, spiritually, emotionally by what we're doing. And if we just think of it as numbers or as technology, we will miss doing them as a proper service. So I think the emotion that comes out of good engineering, and some of the pieces of engineering are mind-blowing and awe-inspiring, should be something that engineers are well aware of. So what's the purpose of 21st century engineering? I think it's very similar to the old Treadgold civils definition, the art of directing the great sources of power in nature for the use and convenience of man. Ed McCann and I rewrote it slightly for structures, the art of changing the physical world for the use and benefit of, I would now say, humanity, for being told off for putting mankind. But it's an art, and it has a physical product. It is not a process. Engineering is not a process. And people who go into engineering thinking they're going to be process operators, I think they should get another job. How does the culture of today's engineering map to the needs of the 21st century? Well, this is a thing we're doing actually with Tim and with John Orr, who are both here, just looking at custom and practice in one little aspect of structural engineering, which is basically how much material people use in practice. And you'd think, because we're taught that there is a theoretical approach to structures, and the answer is basically, for a bending moment in the middle of a beam. There's a single answer under a defined load. You'd think that people would have a consistent set of behaviors responding to that. They don't. And what's fascinating about this report, and I commend it to you to read it, it's just been published, and John, I'm sure, will give you the link if you want it, is that people, by their own admission, do not do what it says in the regulations. They interpret them for reasons best known to themselves to add material. And that's one example of something that is probably not very helpful for the 21st century when we're resource limited. We're looking for people to be smart about the way they use the planet, not to just gild the lily all the time. And I mean, a simple example is loadings, where you know everybody knows that office loadings are bonkers. This is 2.87 kilonewtons a square meter on the Golden Gate Bridge. You know, you couldn't fit any more people on, and yet every single office building all over the world, and thousands of other sorts of buildings, are designed for ridiculous loads, which the building will never see in practice. We've got to stand up. And as academics, it's important to say there is a logical and statistical reason that these are bonkers. And really, it's time for people who have the knowledge to get into the place where they say, okay, let's do something a bit more realistic. Because in the end, the whole planet suffers because we use too much resource. So this, in The Ascent of Rumdoodle, which is the book I quoted from on the lurking suspicion, there's... this more or less sums up my own experience of the state of structural engineering, I'm afraid. To my utter astonishment, there were no obstacles. We were on the summit. For the second time on the expedition, I doubted my own sanity. Remember, I'm talking about structural engineering here. And the name of our company is Expedition. Rumdoodle was 40,500 feet high. Unless my barometer on myself was mad, we were at 35,000. What could have happened? Over to the east, a magnificent mountain stood against the sky. Its glittering summit, 5,000 feet above us, we climbed the wrong mountain. And I do think that's what is happening in education and in practice at the moment. We are going up the wrong mountain. And we can see, in fact, maybe we can't see because it's a bit foggy, but there are other mountains around. And actually, we maybe have to go down to the valley to go up again. And it's tricky. When people have invested a huge amount of effort to get to the top of a mountain, to develop those skills, to actually say, you know what, we're going to have to start again, is really tough. But I do think, as I say, I'm optimistic. I think it's people have the capability, they just need the will and the motivation. What engineering skills, Ian, I said Ian's given my talk for me, he asked the same question. Well, we're all thinking about the same things. What engineering skills are needed for the 21st century? This is Tristram Carfrae, who is up there on the wall as a gold medalist. The importance of, and this is interesting because of the words he uses are actually significant. Creative design and innovation, okay, creativity and innovation. But he talks about instinct, hunch, emotion, more valuable in the future because of automation and artificial intelligence. The human part of what we do becomes more important. I think it's really interesting. This is another world-famous engineer demonstrating, I think he's doing a creativity class on how to 101 uses for a very short length of reinforcement bar with insufficient anchorage lengths. But anyway, he uses the word creative as well. And so how do creative people work? Because if you can get inside their heads, and more importantly, it turns out, inside their environment, then you might have some chance of enabling them to do their stuff properly. And the world needs more creative people. So there's a very good book which looks at the daily rituals of creative people. And, for example, Victor Hugo was awakened by a daily gunshot from the fort. But the orange stuff, all the orange stuff is having meals, talking to friends, not working, basically. The blue stuff is going out for a walk or doing something physical. Again, not working. There's some more. Mozart. Quite often they work in the evenings. They don't work in a physical environment that would be recognizable as an office. So if you think about what that means nowadays, people are working all over the place all the time. And they spend an awful lot of time not working at all, by all accounts. And so we asked the engineers in our practice, this is how they would like to work. this is how they actually work at the moment, which is, you know, you clock on at 9 o'clock, you're allowed out for 20 minutes, you know, and you have to clock back on again at 12:30 or 1 o'clock, and you work until 6 o'clock, then you go home. You're allowed to have dinner with a friend or a husband for an hour, and then you have to disappear off. But there's no time for creativity. It's a regimented thing. She said, because it is a she, it's not Ed McCann, that she would like to have time to work alone on her own, to think. More time for reading, a bike ride, playing games, spending more time talking, and that sort of stuff. And it's the off time that the brain uses to, and the communication with other people to help people become more creative. So basically, it's a shift from the orange, which is regimented, to the green, which is much more free form in terms of the way people are working. 16 years ago, when I was at Imperial, I wrote a book called, a report called Towards a 21st Century Curriculum. It basically mapped the teaching in and I invite academics to map their own courses in the same sort of way. What was taught in the courses, what was actually needed in practice, and how much of it was left to some magical event after people leave university to pick up. And certainly at that time, most of the things that were useful in practice were not taught directly, and it meant you had to do an intensive sort of catch-up. Now, I know that there have been, in the last 16 years, there have been great progress made in design and creativity classes, project-based learning and stuff like that, but I still think it's very weak, and much more to do there. And I think the balance is wrong, frankly. You know, it's... well, you can see. I think there's too much emphasis on the right or wrong theoretical side, and not so much on the things which are contextual. And I put this in. I actually put this in before I realised Ollie was talking later on today. But if you want to know about the sort of state of the art in terms of creative education, there are lots of places to go. But one good place is to go to Ollie's site, which is called Eiffel Lover, or Eiffel Over, and it's called Creative Catalyst. And there are loads of stuff on there about how to look at creativity in a very sort of inventive way. So if you want a bit of stimulation, I recommend that as a source. Or you could talk to Ollie, who's here. Anyway, what sort of engineers does the 21st century need? Well, engineering is done, as I said, it puts physical things on the planet. It's done by people interacting together through projects. This is our sort of standard project process, beginning with the planet needing something and eventually humanity learning from it and feeding it back into the next project. I disagree with Ian. I don't think those two loops are disconnected. I think the analysis is part of the design process, and if you analyze something and find out it doesn't work, you have to go back again and do it again. So this loop, the design loop, conceive, test, analyze, judge, is very, very important. That's where designers earn their trade. I think that it's actually, in trying to work out when you get to here, whether you've got a good answer or not, that's what's tough. So I wanted just to mention a conversation I had with this fellow who's Renzo Piano. We were working on a project, and he said, "Chris, have you ever heard of kalos kai agathos?" I said, "No, I haven't." "What's that?" He said, "Kalos kai agathos." He said, "It's the ancient Greek phrase. It means beautiful on the inside and beautiful on the outside." He said, "That's what I try to do when I'm designing something. Please, can we put that into our project?" It's very, very hard. There are a lot of projects, and some of the ones that Ian showed, I would argue, are beautiful on the outside and fairly ugly on the inside in terms of their conceptual framework. It's really tough to have something which is beautiful all the way through. So an example of something which might qualify is a Stradivarius violin. You know, really brilliant use of materials, makes beautiful music, you know, pared down to absolute beautiful levels of craftsmanship. And it's conceptually very simple. I mean, it's a bit frilly, I suppose, if you wanted to criticize. But we use kalos kai agathos at a summer school we ran inside our own practice. And this little, that prompted a fairly heated debate afterwards about whether using the ancient Greeks to tell modern engineers how to approach the world was any use. And I said, well, I think Renzo Piano knows a thing or two about this, and he is the one who suggested it. But this chap said, no one has said they found the ancient Greek inspiring. For me, I think it's dated. We're stepping back in thought 100 or 200 years. I don't think that, as you can tell. I think that actually there are some things which work quite well over 2,000 years, and they probably worked very well 100,000 years before that, and hopefully they'll work in 100,000 years' time. I think trying to design something which is beautiful, let's say theoretically and conceptually inside, and beautiful outside is something to aspire to, and we should do it. So I disagree with this chap. He's still working for us. It's a very generous organization. There is a correspondent in Latin, which you may have heard, which is more familiar, which is mens sana in corpore sano, which is healthy body and a healthy mind and a healthy body, which is the sort of thing that people try and do for themselves, but I'm arguing we should be doing that for engineering and for the planet. Right, what sort of people might be useful then? So the collaborator. So I was watching a film about the making of a record called The Skeleton Tree by Nick Cave and the Bad Seeds. There's a very nice black and white documentary made a couple of years ago. And in it, Nick Cave sitting at the piano. He has a collaborator called Warren Ellis, who is a multi-instrumentalist. And Nick Cave says something like, the trouble is, if I sit here and play stuff on the piano, it's all predictable. I know, I can't surprise myself. It's impossible. Even if I play something badly, in a way, that's not a surprise. He said, when I play something and then Warren hears it and plays something different back to me, he does something that I couldn't possibly ever have imagined, and he changes the place that we would have got to. I can't do it on my own. He can't do it on his own. Between us, we get somewhere we would never have got on our own. And the collaboration is really, really important. It works in music. It works in engineering. It works in design. It works between consultants and clients as well. And these little diagrams, which are attempt to show, these are projects, beginning to end of projects, and the degree of interaction, and the degree of collaboration that's needed. What's interesting, I'll just summarize it, that if it's a very formulaic project, and everybody knows roughly what the answer is, the degree of collaboration that's needed is relatively small, because everybody knows the answer is more or less a production process. If it's something like Planet Earth trying to deal with climate change, the degree of collaboration is high because no one knows the answer, and you have to talk to your co-conspirators to come up with things that you wouldn't otherwise. No one can do it on their own. So the more unfamiliar the project, and we're facing an awful lot of stuff going forward that's unfamiliar, the higher the degree of collaboration. These are based on a bunch of case studies, and it's a very good. So this is a good equation. It's the only equation in this. Collaboration is inversely proportional to the degree of familiarity with the thing you're grappling with. And there is, again, I would commend this to the academics here. There's an organization called Constructive Collaboration, which has built a bunch of tools which enable people to test out how they're collaborating when they're setting up teams and actually look at ways of improving it. And they have a mission to share their findings for the common good. So they have an academic purpose as well as a sort of industrial purpose. So constructive collaboration, well worth looking up. An example of, so I'm working at the moment with Norman Foster, well-known architect. He draws, so you can collaborate by drawing, you can collaborate by talking, you can collaborate face by face or by telephone, which these came by phone. So he drew away, little tiny building we're trying to do, and I responded with some little sketches to say we could do this or this or this. That's basically one simple form of collaboration, and it still works without computers, face to face. We could have done that at a table. Lots of other ways of doing it, but I do think engineering is a communal activity by and large, and it's got to be taught that way from the beginning. The other thing is engineering projects, and again, there's a very long feedback loop in engineering. Projects take 10 years. So if you're trying to learn, if you're doing a sort of 10,000 hours classic learning thing where you just practice, you can't do many practices in the course of a human life. It's impossible. The projects are too long. So you have to talk to people. So if you're trying to work out how moths get there and you're a small child, you'll probably be 70 by the time you worked out what's going on, because if you try and do it on your own. If you engage with other people, you might find out quicker. So this process that goes from, let's say, trying to do something to learning the outcome and feeding it back in, the feedback loop from previous projects to new ones, you can't do it on your own, on the basis of your own projects. You have to do it by talking to other people. So that's why the collaboration becomes really important, because you get their experience. So use them as a time-traveling machine. You shorten the amount of time between beginning and end of the projects because you overlay multiple project loops. It's really important for engineers. If you just do your own thing, you're going to end up in a back alley very quickly. So what sort of engineers are needed? This is well rehearsed, but I'm going to show it because we use it with student groups very often. Basically, artists, artisan, philosophers are three different strategic approaches to design. And this comes out of observation of lots of designers from lots of different backgrounds, not just engineers. As I'm more sort of slightly artistic. Artisans tend to focus on producing the world's perfect reinforcement drawing or something along those lines. They just try and make things better. They start from something they know and they try and make it slightly better. Philosophers try and understand the whole bloody thing. Big shooting match. This is a philosophical project, if you like, with every single ingredient framing in. A lot of energy involved in that. And Ed McCann, who some of you know, is a more philosophical character. Those three approaches are useless on their own. You can't, if you're trying to do a project and you've only got artists, you're going to end up with something which probably doesn't work. It's going to be too, if you only do what was done yesterday, you're never going to innovate. And if you only think about you try and get a framework of everything, you're bound to miss something, and your philosophical conception is going to be wrong. You need all three sorts of people on projects. So we have. There's a little test actually you can do, which is published in various places, to find out which of those you are. But we recommend that in project teams at university and in practice, you try to get a mix of people with an artistic approach, people with an artisan approach, and people with a philosophical approach. And the reason for that is that they work differently on different sorts of projects, so different parts of the project. So philosophers are very good at understanding what the need is, for example. You might say more artistic people are quite good at conceiving things, although artisans are very good because they bring in research from, they study and study and study and say, well, you could try that, they did that over there. And actually artificial machine learning comes in here nowadays. And that analytical stuff, which is, let's say, if you like, is an artisan thing. It's something which is a more formulaic process, but actually you learning to do it very well. It probably sits in there. Judgment is, again, more philosophical. You can apply it to making and using as well, and also learning. So each of the parts of the project requires a different sort of skill set. And if you put an artist into the position of testing, they're only likely to test things on a very small subset of what might be needed. You actually need all three things. The second part of what sorts of engineer are needed, and this is also useful in terms of academic projects and real projects, are specialists and specialist generalists. So specialists are people who specialize in specialisms, in being specialists. So like, for example, doing CFD work or fantastic dynamic studies or whatever, understanding how carbon fiber maps to stainless steel. Specialist generalists are people, so Brunel is a specialist generalist, someone who specializes in being generalist, and they try to understand everything, and they try and join it together. So if this is the world and what the world needs, here are all the possible specialists who might be able to map to what the world needs. The specialist sits in the middle here, trying to join the needs of the world to the capabilities of the specialist. And it's an integrating job. It's really, and now, actually what we have is this, where we have a bunch of specialists who are maybe fantastic at what they're doing, and a bunch of needs over here, but they're not necessarily joined together because we don't have enough people in the specialist generalist role in the middle. And engineers, like Brunel, are that sort of character. We need more of those, so please educate those as well. for which you need, and an example of where that didn't work, so this is a fireman at the Grenfell Tower afterwards, that is a project where all of the specialists, if those of you who from other countries, there was a big fire in a tower block caused by a failure of the design and construction of a retrofit cladding system, and that there were gaps in that process all the way through because it wasn't properly integrated. And no matter how good or bad the specialists were, they weren't all in the right place at the right time, and they weren't joined together, as a result of which the building burned and lots of people died. So I do think there's an opportunity, and Grenfell is a really good thing. It's a really good thing. So you say 3 or 5? You went on far too long, I think, if I remember rightly. Okay, I'm going to move on. This is my idealized shape of a project team, which is to say lots of T-shaped people. So these are people who are specialists but have a bit of knowledge to link them to their mates. But instead of the people on the end not having anybody to talk to, actually joining them, enabling the T-shaped people to join together into a sphere, diatomic technologist sort of character. I'm going to move quickly forward if you're only going to give me 3 minutes. The obvious sort of emergent engineering entity is humanity and machine together. So old-fashioned versions look like this. The tools we now have are more computing and brains. I think the practicality and the physicality of it is something which is very important. You get a lot of pleasure after just making something and putting it on planet Earth, and I think we shouldn't forget that. When you see these things flying about, it's with a massive bit of kit. It tickles people. Patient practice is something which I've said it has a very long feedback loop, and therefore you need collaboration. The tools that are available are not traditional tools. I think in order to learn how to collaborate, it's best doing it in a way where the consequences of it not working are not very severe. So playing is really important. I think that enabling these are really expert designers messing about, trying to do stuff. And as a result of that, they build up confidence in each other, at which point they're more likely to collaborate better. Drawing is really important. These books, drawing as a way of playing for engineers is really important. Sketching, both for yourself and for other people, is really important. Trial and error, making stuff, messing about. I just think I can't overemphasize learning how to fail. And I'm not going to show this, but some of you will know Gennaro Senatori's adaptive truss, which is something which is an infinitely stiff system, like the human arm. That's an experimental project which doesn't have a use at the moment, but we would love to find more experiments like that of a practical nature in university. Practice is, if you play sport or you play in a band, it's the same. I coach rugby, and I try and teach them how to do scissors and switch moves and everything else by practice, and to the point that it becomes second nature, at which point then they can improvise. That's what engineers need to be able to do. Practice until it's second nature, and then you can improvise. And I'm going to finish with this slide, which is a very complicated slide, but I'll explain what it is. This is an attempt to convert the 4-year undergraduate program in civil engineering at University College London into a patient practice project-based program, stitching together the theoretical, the practical, and the conceptual, and groups and collaboration. And the basic thing that I gave this to Tim, and he looked at me as I was mad because he couldn't understand it, so I'm going to try and explain it briefly. This is the project, so it begins with a need, ends up with feedback loop, conceive, test, judge, design loop. So it's that same diagram that I just showed you, but vertical down the side here. These are 4 years worth of activities at university. And the key thing is, the students at any point are told where they are on this diagram. So if they're learning a series of tests or something, which is a theoretical part of the course, you say, okay, you're here now. We're now doing testing. There. Here we're doing a conceptual piece. Up there. Here we're doing a making piece. And it goes, and because of the need for practice and doing it more than once and learning by practice, this cycle happens over and over. So it's not a linear process, it goes up and down. So I tried to get that going at UCL, it was, let's say, a partial success. I've tried to get it going at Imperial, it was a partial success. I'm sure that Tim and others have tried to get it going in various places, it's been a partial success. But this stitches theoretical teaching, practical teaching, collaboration into one holistic thing. It probably could draw it better, but that's what I'd say would be a good tool to achieve some of the things I was talking about earlier. Thank you very much.
Chris, thank you.